Right now, as you watch this, there could be entire worlds brushing against ours, realms folded into space itself, invisible yet closer than your next breath. We think we know the universe, but what if everything we see is just a fraction of reality? Picture this: dimensions curled up like tiny, invisible threads, or parallel universes stacked like pages in a cosmic book. These aren't just sci-fi fantasies, they're serious theories shaping modern physics. From the mind-bending math of string theory to the holographic principle that suggests our 3D world might be a projection, scientists are racing to uncover the universe's best-kept secrets. And here's the wild part: if these hidden dimensions exist, they could rewrite the rules of reality itself. So buckle up, we're about to dive into 30 theories that will stretch your mind beyond the limits of space and time. By the end, you might never look at the universe the same way again. Now, let's unravel the first mind-bending theory: string theory's hidden dimensions. Imagine the universe isn't made of tiny dots, but of vibrating strings, like microscopic guitar strings playing the symphony of reality. These strings don't just wiggle in the 3 dimensions we know: up, down, left, right, and forward, backward. Instead, string theory suggests there could be 10 or even 11 dimensions, with 6 or 7 curled up so tightly they're invisible to us, like a crumpled piece of paper seen from far away. Here's why this matters: these extra dimensions might be the missing puzzle piece to unite quantum mechanics, the rules of the very small, with gravity, the force that shapes the cosmos. In our everyday world, gravity feels weak compared to other forces. Think of how a tiny magnet can overpower Earth's entire gravitational pull. But in string theory, gravity's feebleness could be an illusion. If gravity's particles, called gravitons, leak into these hidden dimensions, it would explain why gravity seems diluted in our 3D experience. The math behind this is elegant but wild. Those vibrating strings can't just move anyhow, their harmonies are tied to the shape of those curled-up dimensions. Picture a flute playing different notes depending on how its holes are arranged. Similarly, the way these extra dimensions fold and twist could determine everything from the mass of particles to the very laws of physics. And here's the kicker: if string theory is right, it wouldn't just add dimensions, it could rewrite our understanding of reality's fabric. Suddenly, the universe isn't just a stage for particles, it's a cosmic orchestra with hidden dimensions conducting the show. Up next, we'll explore how this idea expands into an even grander vision: the multiverse. Now, let's take string theory's hidden dimensions and stretch them even further into the mind-blowing realm of M-theory. Think of it as string theory's bigger, bolder sibling. While string theory dances with 10 dimensions, M-theory adds an 11th, weaving a cosmic tapestry where the universe isn't just strings but vast, floating membranes, or branes for short. Picture these branes as invisible sheets, each potentially hosting its own universe, drifting through higher dimensional space like pages in a boundless book. Here's where it gets wild: our entire universe might just be one of these branes, a 3-dimensional island in an 11-dimensional sea, and if branes can collide, that's where the magic happens. Some scientists propose that the Big Bang itself could have been a cosmic car crash, a violent meeting of 2 branes that unleashed the energy to birth our universe. It's like shaking a snow globe, but instead of glitter, you get galaxies, stars, and everything we know. But M-theory doesn't stop there. If branes can collide once, why not over and over? This opens the door to a cyclical multiverse where universes are born, expand, and eventually collide again in an endless cosmic dance. No need for a single, mysterious starting point, just an infinite loop of creation. And here's the kicker: if other branes exist parallel to ours, they could have entirely different laws of physics. Some might be barren, while others could teem with life we can't even imagine. It's a humbling thought that our universe might be just one note in a symphony of realities. Up next, we'll rewind to an early blueprint for hidden dimensions, the Kaluza-Klein theory, and see how it set the stage for today's cosmic mysteries. Before M-theory and its cosmic brains, there was another daring idea that first cracked open the door to hidden dimensions. Let's step back in time to the early 1900s, when two brilliant minds, Theodore Kaluza and Oskar Klein, proposed something revolutionary. What if gravity and electromagnetism, the only two forces known at the time, weren't separate at all? What if they were just different faces of the same phenomenon, glimpsed through an unseen fifth dimension? Kaluza's math was elegant. By adding just one extra dimension to Einstein's equations of general relativity, he showed that electromagnetism could emerge naturally, like a shadow cast by gravity in higher dimensional space. Imagine rolling up a piece of paper so tightly you can't see its edges. That's how Klein suggested this fifth dimension might be hidden, curled into a loop smaller than an atom. To us, it would be invisible, but its effects would ripple through our universe, tying together forces that seemed unrelated. For a moment, physicists were electrified. Here was a theory that could unify the known forces under a single geometric framework, a dream that still drives physics today, but the excitement didn't last. When quantum mechanics exploded onto the scene, Kaluza-Klein's elegant fifth dimension struggled to explain the messy new particles and interactions being discovered. Without experimental proof, the theory faded into the background, seen as a beautiful but incomplete idea. Yet its legacy is undeniable. Kaluza-Klein's bold leap into higher dimensions planted seeds for string theory, branes, and even the holographic principle. It showed that hidden dimensions weren't just science fiction, they could be tools to solve physics' greatest puzzles. And who knows, with new experiments probing the fabric of reality, this century-old theory might yet have surprises left to reveal. Next, we'll explore how modern physicists revived these ideas in the brane world scenario, giving hidden dimensions a thrilling new twist. Now, let's leap into a modern twist on hidden dimensions, one that turns our entire universe into a cosmic island adrift in something far stranger. Picture this: what if everything we know, every star, every planet, even you and me, exists on a vast three-dimensional membrane, or brane, floating like a sheet of paper in a higher dimensional space? This is the brane world scenario, a bold idea that reimagines reality itself. Here's the mind-bending part. In this model, gravity isn't confined to our brain like the other forces. Instead, it's free to spread into the bulk, the higher dimensional space around us. Think of it like this: if our universe is a slice of bread in a multidimensional loaf, gravity is the aroma wafting through the entire kitchen, while other forces like electromagnetism stay stuck to the slice. This could explain why gravity feels so weak compared to the other forces. It's literally diluted across dimensions we can't see. But how do we test such a wild idea? Enter the Large Hadron Collider. Scientists have speculated that if extra dimensions exist, the collider might produce tiny, fleeting black holes or particles carrying energy that seems to vanish into hidden realms. So far, no smoking gun has appeared, but the search isn't over. Every new experiment inches us closer to answering whether we're living on a brane, and whether gravity's secrets lie just beyond the edges of our perception. What's thrilling is how this idea ties back to Kaluza-Klein's vision. Both theories use hidden dimensions to solve cosmic puzzles, but the brane world scenario takes it further, suggesting our entire universe might be a tiny part of something unimaginably larger. Next, we'll dive into an even more radical idea: the holographic principle, where our three-dimensional reality could be nothing more than a projection from a distant two-dimensional edge. Now, let's stretch our imaginations even further with a concept so radical, it turns our understanding of reality inside out. What if everything we experience, every galaxy, every mountain, even the screen you're staring at right now, is nothing more than a hologram? Not the sci-fi kind, but a cosmic projection, like a movie playing on the surface of a distant, two-dimensional boundary. This is the holographic principle, and it might just be the key to unlocking some of the universe's deepest mysteries. Here's how it works. Imagine a black hole, one of the most extreme objects in the cosmos. When matter falls in, it doesn't just vanish, it leaves behind a kind of imprint on the black hole's event horizon, the point of no return. In the 1990s, physicists Leonard Susskind and Gerard T. Hooft realized something astonishing. All the information about what falls into a black hole could be encoded on its two-dimensional surface like a cosmic hard drive. From there, the leap wasn't far. What if our entire universe works the same way? This idea ties directly into quantum gravity, the quest to unite Einstein's theory of relativity with quantum mechanics. In a holographic universe, the three-dimensional world we perceive could be a kind of illusion, with the real action happening on a distant 2D boundary we can't see. It's like watching a 3D movie. The depth feels real, but it's all coming from flat data on the projector. The implications are staggering. If the holographic principle is true, it could explain why the universe seems so finely tuned, or even why time flows in one direction. It's a theory that bridges the very large black holes and the very small quantum particles, offering a fresh lens to view the cosmos. And while it's still speculative, experiments with quantum entanglement and high-energy physics are starting to test its wild predictions. Up next, we'll shift gears to another mind-bending model, one where the universe isn't just expanding, but cycling through endless rebirths. The cyclic universe theory suggests hidden dimensions might be the engine behind this cosmic reset button. But what if the universe isn't a one-time event? What if the Big Bang wasn't the beginning, but just one chapter in an endless cosmic story? This brings us to the cyclic universe model, a theory where hidden dimensions act like a cosmic reset button, triggering cycles of creation and destruction over unimaginable timescales. Picture this: instead of a single explosive beginning, our universe might be caught in an eternal dance with another parallel reality, a neighboring brane floating in higher dimensional space. According to physicists like Paul Steinhardt, these branes could periodically collide, releasing enormous energy that fuels a new Big Bang. The universe expands, cools, and evolves, just like ours, until gravity eventually pulls everything back together, leading to another collision and another rebirth. No beginning, no end, just an infinite loop of cosmic renewal. This idea challenges the more popular inflation theory, which suggests the universe ballooned rapidly just after the Big Bang. Steinhardt and others argue that the cyclic model solves some of inflation's puzzles, like why the universe appears so uniform. Each collision would wipe the slate clean, smoothing out irregularities from the previous cycle. The hidden dimensions here aren't just mathematical curiosities. They're the stage for this grand cosmic drama. Without them, the branes couldn't move or collide in the way the theory requires. And while we can't yet observe these higher dimensions directly, the cyclic model makes testable predictions, like faint gravitational wave patterns that future telescopes might detect. So, is our universe destined to repeat itself forever? It's a breathtaking possibility, one that turns the idea of a linear timeline on its head. Next up, we'll explore how hidden dimensions might also hold the key to another cosmic mystery, the strange, invisible particles known as dark matter. Now, let's shift our gaze to a theory that might just hold the missing pieces to one of the universe's greatest puzzles. Supersymmetry, often called SUSY for short, proposes that every particle we know has a hidden twin, a superpartner lurking in higher dimensions. Imagine a cosmic mirror where electrons, quarks, and even photons have shadowy counterparts with strange new properties. These superparticles could be the key to unlocking dark matter, the invisible glue holding galaxies together. Here's why this matters. If supersymmetry is real, these extra particles would balance the equations of quantum physics in a way that makes our current theories click into place. The lightest superpartner, often dubbed the neutralino, is a prime candidate for dark matter. It wouldn't interact with light, just like the mysterious substance we've detected only through gravity. But there's a catch. Despite decades of searching, particle colliders like the Large Hadron Collider haven't found a shred of evidence for these superpartners. Some physicists argue we might need even more powerful machines to spot them, while others wonder if supersymmetry's hidden dimensions are curled up in ways we can't yet probe. It's a high-stakes game of hide and seek, where the rules of reality itself might be rewritten. Next, we'll dive into another bold idea: how warped extra dimensions could explain why gravity is so weak compared to other forces. Now, let's step into a world where space itself bends in ways that challenge everything we thought we knew about gravity. The Randall-Sundrum models, named after physicists Lisa Randall and Randall-Sundrum, offer a stunning solution to one of physics' biggest head-scratchers: why gravity is so incredibly weak compared to other forces like electromagnetism. Picture this: our universe might be a floating membrane, or brane, nestled within a higher dimensional space where gravity's strength is diluted by the warped geometry of these hidden dimensions. The first model, RS1, proposes two branes separated by a tiny but warped fifth dimension. On one brane, gravity is naturally strong, but on ours, the weak brane, it's stretched thin, explaining why we experience it as feeble. This setup also suggests that tiny ripples in gravity could leak into our world as exotic particles, potentially detectable in particle colliders. Then there's RS2, a sleeker version where our brain sits alone in an infinite warped dimension. Here, gravity's weakness comes from its intensity fading rapidly as it spreads away from our brain, like a flashlight beam dimming in a vast, curved hallway. What makes these models so thrilling is their potential to unite quantum mechanics and gravity without requiring extra particles, unlike supersymmetry. But they're not without controversy. If RS1 is correct, miniature black holes might pop into existence at the Large Hadron Collider, a dramatic but so far elusive prediction. Meanwhile, RS2 Infinite Dimension raises wild questions about whether other branes could be lurking just out of reach, each with their own alternate physics. Up next, we'll explore how these hidden dimensions might reshape the very fabric of spacetime at the quantum level, where gravity and particles dance in ways we're only beginning to imagine. Now, let's take a closer look at how gravity itself might behave when it steps into the hidden dimensions we've been exploring. Quantum gravity is one of the most elusive puzzles in physics, and extra dimensions could hold the key to solving it. Theories like loop quantum gravity suggest that at the tiniest scales, think a billionth of the size of an atom, space-time might not be smooth and continuous as we imagine, but instead made up of tiny, woven loops. Now, throw extra dimensions into the mix and things get even more fascinating. In higher dimensions, these loops could twist and interact in ways that smooth out the jagged edges of quantum gravity, creating a more unified picture of spacetime. Imagine a tangled ball of yarn. If you add more dimensions to work with, the knots might loosen, revealing a cleaner structure underneath. This could help bridge the gap between the chaotic quantum world and the orderly force of gravity. Some physicists speculate that in higher dimensions, gravity might not be a force at all, but a natural consequence of spacetime's geometry, like how a ball rolls downhill not because it's being pulled, but because the ground slopes. If true, this could explain why gravity feels so different from other forces, and why it's been so hard to fit into the quantum framework. Up next, we'll dive into an even bolder idea. What if dark matter isn't missing at all, but simply hiding in these extra dimensions just out of our reach? Here's where things take a fascinating turn. What if dark matter isn't some exotic, invisible substance, but something far more ordinary, just lurking in a dimension we can't see? Picture this: our universe is like a sheet of paper, and right next to it, another sheet floats in higher dimensional space. matter on that neighboring sheet would still tug on ours through gravity, but light, the messenger of every other force, wouldn't cross the gap. To us, that matter would be invisible, detectable only by its gravitational pull. This idea flips the script on dark matter. Instead of hunting for mysterious particles, we might be feeling the gravitational echoes of entire stars, planets, or even civilizations in a parallel dimension. Think of it like hearing footsteps in the apartment above you. You can't see the neighbor, but you know they're there. Some theories suggest these hidden dimensions could be curled up incredibly small, or stretched vast but just out of reach, leaving dark matter's fingerprints all over our cosmos. And here's the kicker. If dark matter is just regular matter in another dimension, it could explain why it doesn't interact with light or collide with our atoms the way normal matter does. It's not ignoring the rules, it's playing by a different set in a game we're only beginning to understand. Up next, we'll challenge another fundamental assumption. What if time isn't just a one-way street, but a dimension with hidden layers of its own? Now, let's twist our perspective even further. What if time isn't just the steady tick of a clock, but a dimension with hidden depths? We're used to thinking of time as a straight line, moving relentlessly from past to future. But some theories suggest it could be far more complex, like a branching river or a tangled thread in higher dimensional space. Imagine time not as a single path, but as a landscape where every possible past, present, and future exists simultaneously. This idea isn't just science fiction. In physics, closed time-like curves, loops where time circles back on itself, are mathematically possible in certain space-time geometries. Picture a hiker walking a mountain trail that somehow brings them back to their starting point without retracing their steps. In theory, time could do the same, creating paradoxes where events influence their own causes. Some models even propose that alternate timelines might exist as parallel layers in higher dimensions, like pages in a book we can't flip through. And here's where it gets wild. If time is multidimensional, it could explain why we perceive it as flowing in one direction. Just as a river follows the path of least resistance, our experience of time might be a slice of a much richer structure, shaped by hidden dimensional folds. This could redefine everything from free will to the nature of reality itself. Up next, we'll shrink the cosmic scale to explore how tiny, curled-up dimensions might hold the key to the universe's deepest secrets. Now, let's zoom way into a realm so small it defies imagination. Hidden within every point of our familiar three-dimensional space could be a labyrinth of curled-up dimensions, twisted into shapes so intricate they look like abstract sculptures. These are Kaluza-Klein manifolds, the geometric masterpieces at the heart of string theory. Picture a garden hose. From far away, it looks like a simple line, but up close, you see it's actually a cylinder. In the same way, these extra dimensions might be invisibly coiled into complex patterns a billion times smaller than an atom. What's astonishing is how these tiny shapes could dictate the universe's rules. The way a Kaluza-Klein manifold folds and loops determines how strings, the fundamental threads of reality, vibrate within it. Just as the shape of a violin affects its sound, the geometry of these hidden dimensions could define the properties of particles. One twist might give rise to an electron's mass, another to the photon's lack of it. Even the number of particle generations in nature might be written into these folds. Here's the kicker. If we could peer into this subatomic origami, we might finally understand why our universe has the forces and particles it does. Different Kaluza-Klein shapes would create entirely different physics, meaning our cosmos might be just one possible configuration in a vast landscape of potential realities. It's a humbling thought. The entire diversity of matter might hinge on geometry we can't even see. Next, we'll dive into a theory where these hidden dimensions aren't just static. They could collide, sparking universes into existence. But what if the birth of our universe wasn't a fiery explosion but a cosmic collision? Enter the ekpyrotic universe theory, a bold idea that rewrites the origin story of everything. Imagine two vast, parallel membranes floating in a higher dimensional space, slowly drifting toward each other. When they finally collide, the energy of that impact doesn't destroy them. Instead, it ignites the creation of our entire universe like a spark lighting a cosmic fire. This isn't just a wild guess. The ekpyrotic model offers a sleek alternative to cosmic inflation, solving some of its biggest puzzles. For one, it explains why the universe appears so uniform. Instead of stretching space faster than light to smooth things out, the ekpyrotic scenario suggests those colliding branes were already perfectly aligned, transferring their symmetry to our newborn cosmos. And here's where it gets even more intriguing. Unlike the one-and-done Big Bang, this theory ties into the cyclic universe idea we explored earlier. Those same branes could rebound after collision, pulling apart and then crashing together again, potentially setting off endless cycles of creation. But how does it stack up against inflation? While inflation relies on a mysterious energy field to drive expansion, the ekpyrotic model leans on the geometry of higher dimensions. One key difference is the way each handles cosmic wrinkles, the tiny density variations that seeded galaxies. Inflation stretches quantum fluctuations into large-scale structures, while the ekpyrotic scenario suggests those wrinkles came from imperfections in the branes themselves. The real beauty of this idea, it turns the universe into a cosmic accordion, with collisions breathing new life into existence over and over. And if we're lucky, future experiments might catch whispers of that ancient collision in the cosmic microwave background, hints that our universe began not with a bang but with a bounce. Next, we'll venture into one of the most enigmatic places in existence, where hidden dimensions might warp space so severely they tear open portals to other realities. Now, let's turn our gaze to one of the most mysterious phenomena in the cosmos: black holes. These cosmic behemoths don't just warp space and time, they might actually tear holes in the fabric of reality itself. Could black holes be secret passageways to other dimensions or even parallel universes? It's a question that pushes the boundaries of both science and imagination. At the heart of this idea is the concept of wormholes, hypothetical tunnels through space-time that could connect distant regions or even different universes. Einstein's theory of general relativity doesn't rule them out, but here's the twist. Traversable wormholes would require exotic matter with negative energy to stay open, something we've never observed. That's where black holes come in. Some theories suggest that the singularity at a black hole's core, a point of infinite density, might not be a dead end but a gateway. This idea gets even wilder when we bring in ER equals EPR, a theory proposed by physicists Leonard Susskind and Juan Maldacena. It suggests that entangled particles, those spooky, instantaneously connected quantum partners, might be linked by microscopic wormholes. If that's true, then black holes, which are thought to trap entangled particles, could be cosmic versions of these quantum bridges. But before you pack your bags for an interdimensional voyage, there's a catch. Crossing a black hole's event horizon is a one-way trip, at least for now. The intense gravitational forces would stretch and compress anything entering in a process called spaghettification. Yet, some theories speculate that advanced civilizations might harness black holes as shortcuts through space-time, or that information swallowed by a black hole could re-emerge in another universe. The real challenge testing these ideas: black holes are notoriously secretive, hiding their inner workings behind their event horizons. But future breakthroughs in quantum gravity or even gravitational wave astronomy might one day reveal whether these cosmic monsters are truly portals to the unknown. Next, we'll explore an even more radical thought: what if dimensions themselves vanish at the smallest scales, rewriting the rules of reality? Now, let's take a sharp turn into the quantum realm, where the rules of reality start to bend in ways that defy our everyday intuition. Imagine shrinking down to the smallest possible scales, where particles flicker in and out of existence, and space itself might not behave the way we expect. Here, some physicists propose a mind-bending possibility. Dimensions themselves could vanish. This idea flips traditional thinking on its head. We're used to living in a world with 3 dimensions of space and 1 of time, but at the quantum level, things might be simpler, not more complex. The controversial theory suggests that when you zoom into distances 1 trillion times smaller than an atom, dimensions could dissolve away, leaving behind a more straightforward framework for quantum gravity. Why would dimensions disappear? Think of it like this. When you look at a mountain from afar, you see its jagged peaks and valleys, a complex 3-dimensional shape. But if you zoom in close enough, the surface might appear smooth, even flat. Similarly, at the tiniest scales, the intricate structure of space-time could simplify, making gravity easier to reconcile with quantum mechanics. This isn't just wild speculation. Some approaches to quantum gravity, like causal dynamical triangulations, rely on this very idea. They suggest that space-time at the Planck scale, the smallest meaningful size in physics, might be 2-dimensional or even fractal, shedding dimensions to avoid mathematical chaos. It's a radical departure from string theory's extra dimensions, but it offers a tantalizing solution to one of physics' biggest headaches. Of course, not everyone's convinced. Critics argue that vanishing dimensions would require rewriting fundamental laws in ways we can't yet test. But if future experiments, perhaps with ultra-precise particle colliders or quantum sensors, find hints of this dimensional dropout, it could revolutionize our understanding of reality's deepest layers. Next, we'll venture into another twist in the cosmic puzzle, mirror universes hiding in plain sight within higher dimensions. Now, let's stretch our imaginations even further into the realm of mirror universes, a concept that sounds like science fiction but has serious scientific roots. Picture our universe as just one reflection in a cosmic hall of mirrors, where countless parallel realities exist alongside ours, each with its own tweaked version of physical laws. The idea hinges on higher dimensions acting like a hidden canvas where these mirror universes could reside. Unlike the multiverse theories that suggest separate bubbles of space-time, mirror universes might share the same higher dimensional space but be flipped in some fundamental way. For instance, what if there's a universe where gravity is slightly stronger or where atoms are built differently? These mirrored realities could be just a dimension away, yet completely invisible to us. One compelling version of this comes from string theory, where certain mathematical symmetries predict the existence of mirror particles, shadowy counterparts to every particle we know. If these particles exist, they could form entire mirror galaxies, stars, and even civilizations, all interacting with our world only through gravity. That might explain why we can't see them. Their light and other forces don't cross into our dimensional slice, but how would such a universe even form? Some theories suggest that during the Big Bang, higher dimensional space could have folded in a way that created symmetrical twin universes. Others propose that quantum fluctuations in extra dimensions might spawn these mirror realities naturally. Either way, the implications are staggering. A mirror universe might have opposite charges, reversed time, or even entirely new forces we've never encountered. Of course, proving any of this is a monumental challenge. Detecting a universe that doesn't share our electromagnetic spectrum or nuclear forces would require entirely new methods, perhaps by spotting gravitational anomalies or unexplained cosmic patterns. Yet, if mirror universes are real, they'd rewrite not just physics but our understanding of existence itself. Up next, we'll unravel an even stranger twist. What if space-time isn't smooth but fractal, with hidden layers shaping reality itself? Now, let's take a step into the mind-bending world of fractal space-time, a theory that suggests the fabric of reality might be far more intricate than we ever imagined. Picture space-time not as a smooth, continuous sheet, but as an endlessly complex fractal pattern, repeating itself at every scale, from the tiniest quantum fluctuations to the vast expanse of the cosmos. This idea flips traditional physics on its head. Instead of dimensions being neatly organized, fractal space-time proposes that hidden layers of structure exist within dimensions themselves, like a cosmic Russian nesting doll. At the quantum level, this could explain why particles behave so unpredictably. Their movements might be tracing paths through these fractal folds. On a grander scale, it could even influence how the universe expands, with hidden geometric patterns guiding the growth of galaxies. One of the most fascinating aspects of this theory is how it bridges the gap between quantum mechanics and general relativity. In a fractal universe, the chaotic behavior of tiny particles and the smooth curvature of space-time around massive objects might simply be two sides of the same coin. The fractal geometry could provide a hidden framework that unites these seemingly contradictory worlds. But how would such a structure emerge? Some researchers suggest that the early universe's extreme energy conditions might have imprinted this fractal pattern into space-time itself, like wrinkles frozen into fabric. Others propose that quantum entanglement, the mysterious link between particles, could be a signature of this deeper fractal geometry, with entangled particles connected through hidden dimensional layers. Of course, testing this idea isn't easy. Fractal space-time would leave subtle fingerprints, like slight deviations in the way light travels across the universe or anomalies in the cosmic microwave background. If proven, though, it would revolutionize our understanding of reality, revealing a universe far more intricate and interconnected than we ever dreamed. Up next, we'll explore an even more provocative question. Could hidden dimensions hold the key to the Fermi paradox, explaining why we seem so alone in the cosmos? Now, let's turn our attention to one of the most puzzling mysteries in the cosmos, the Fermi paradox. If the universe is so vast and ancient, why haven't we encountered any signs of intelligent life? Hidden dimensions might hold the answer. Imagine civilizations far more advanced than ours, not just in technology but in their understanding of reality itself. If they've learned to manipulate higher dimensions, they could exist right alongside us, completely undetectable by our three-dimensional tools. Think of it like ants on a sheet of paper, unaware of the humans walking above them. To us, these civilizations might as well be ghosts, their presence hidden in folds of space we can't perceive. This idea flips the Fermi paradox on its head. Instead of asking why we're alone, we might consider that we're simply not equipped to see our cosmic neighbors. Higher dimensions could offer shortcuts for travel, cloaking devices, or even entirely new forms of energy, all of which would make advanced life invisible to our current methods of detection. Some theories suggest that dark matter or dark energy, those enigmatic forces shaping the universe, could be side effects of higher dimensional activity. If civilizations have tapped into these dimensions, their technology might interact with gravity or space-time in ways we can't yet measure. Of course, this raises even bigger questions. If such civilizations exist, are they observing us? Could they be waiting for humanity to reach a certain level of understanding before making contact? Or are we, in our three-dimensional bubble, simply irrelevant to beings operating on a grander scale? The search for answers continues, but one thing is clear: hidden dimensions could rewrite not just physics but our place in the cosmos. Up next, we'll venture into an even more speculative idea. What if consciousness itself is a higher dimensional phenomenon? Now, let's take a step into one of the most mind-bending ideas yet. What if consciousness isn't just a product of our brains, but something that stretches beyond the three dimensions we know? Some physicists and philosophers propose that consciousness itself might be a higher dimensional phenomenon, woven into the fabric of the universe in ways we're only beginning to grasp. Think of your mind not as a closed system inside your skull, but as a receiver tuning into signals from dimensions we can't yet perceive. This idea suggests that our thoughts, emotions, and even our sense of self could be influenced by, or even originate from, realities beyond our own. It's like a radio picking up stations from invisible waves in the air. This theory challenges the traditional view that consciousness is purely a biological process. Instead, it opens the door to wild possibilities like near-death experiences or mystical states of awareness being glimpses into these hidden dimensions. Could déjà vu, intuition, or even dreams be subtle interactions with a deeper layer of reality? Some researchers point to quantum mechanics as a clue. At the smallest scales, particles behave in ways that seem to defy logic, almost as if they're responding to influences outside our dimensional framework. If consciousness operates on a similar level, it might explain why it feels so elusive to science. We've been looking for it in the wrong places. Of course, this is still speculative territory. But if true, it would mean that every thought you've ever had might ripple through dimensions you can't see, connecting you to something far grander than the physical world. Up next, we'll explore another fascinating twist: how quantum entanglements, spooky action at a distance, could be mediated through these very same hidden dimensions. Now, let's unravel another layer of the cosmic puzzle. What if quantum entanglement, that eerie connection between particles across vast distances, isn't just strange but multidimensional? Imagine two particles instantly influencing each other, no matter how far apart they are, as if space itself doesn't apply to them. This spooky action at a distance, as Einstein called it, might not be spooky at all if hidden dimensions are pulling the strings behind the scenes. Here's the twist: instead of particles communicating faster than light, which physics says is impossible, they could be linked through a higher dimensional shortcut, like tunnels weaving through the fabric of reality. Picture ants on a piece of paper. To them, moving from one corner to another means crossing the entire page. But if the paper is folded, bringing those corners together in a third dimension, the ants could touch instantly. That's how entangled particles might talk without breaking cosmic speed limits. Some theories suggest these hidden dimensions aren't just mathematical quirks but active highways for quantum information. When particles become entangled, their states could be synchronized through vibrations or interactions in these unseen layers, bypassing our familiar 3D space entirely. It's as if the universe has a backstage area where the rules are different, and entanglement is the show playing out there. This idea isn't just wild speculation. It could solve one of quantum mechanics' biggest headaches: non-locality. If particles aren't truly separated but connected through extra dimensions, their coordinated behavior makes sudden sense. Experiments like the Bell tests already prove entanglement is real. Now, physicists are asking how it works. Could hidden dimensions be the missing piece? Of course, this raises even bigger questions. If entanglement threads through higher dimensions, what else might? Could time, gravity, or even dark matter be tapping into the same hidden network? The answers might rewrite not just quantum theory, but our entire understanding of reality. Up next, we'll dive into another electrifying idea: how the speed of light itself could behave differently in these hidden dimensions, warping the rules of the cosmos as we know them. Now let's shift gears to a mind-bending possibility. What if the speed of light, that universal constant we take for granted, isn't so constant after all? Imagine light racing through hidden dimensions at different speeds, like a car switching lanes on a cosmic highway. This isn't just science fiction. Some theories suggest that in higher dimensions, light might not play by the rules we're used to. Here's why this matters. In our three-dimensional world, light speed is locked at around 300,000 kilometers per second. But if extra dimensions exist, they could warp the very fabric of space-time, allowing light to travel faster or slower there. Think of it like sound. It moves differently through air, water, or steel. Light in higher dimensions might have its own medium that changes its pace. This idea could solve one of cosmology's biggest head-scratchers: cosmic inflation. That's the moment right after the Big Bang when the universe expanded faster than light itself. How, if light was slower in those hidden dimensions, inflation wouldn't have to break any rules? It could just be tapping into a deeper layer of reality where the limits are different. But wait, there's more. If light speed isn't fixed across dimensions, it might explain why gravity seems so weak compared to other forces. Gravity could be leaking into higher dimensions where light moves differently, diluting its strength in our world. It's like trying to hear a whisper in a windy room. The signal gets lost in the noise of the cosmos. Of course, testing this isn't easy. We'd need to catch light in the act of bending the rules, maybe by studying distant supernova or the echoes of the Big Bang. But if we ever do, it could rewrite physics textbooks and our understanding of reality itself. Up next, we'll explore how gravity's messenger, the graviton, might be slipping into these hidden dimensions, leaving clues about the universe's deepest secrets. Now, let's turn our attention to gravity's elusive messenger, the graviton. Picture this: while light and other forces are confined to our three-dimensional world, gravity might be slipping through the cracks, escaping into hidden dimensions. That's the core idea behind graviton propagation in bulk dimensions. Here's how it works. In our everyday experience, gravity feels weak compared to forces like electromagnetism. A tiny fridge magnet can defy Earth's entire gravitational pull, so why the imbalance? One compelling theory suggests that gravitons, the hypothetical particles carrying gravity, aren't just sticking to our familiar three dimensions. Instead, they're leaking into higher dimensional space like water seeping through a sieve. The more dimensions they spread into, the more diluted their effect becomes in our world. Think of it like a radio signal. If you're standing right next to the speaker, the sound is loud and clear. But if the signal starts leaking into other rooms, the volume drops where you're standing. Similarly, if gravitons are spreading into extra dimensions, their signal in our universe would weaken, explaining why gravity seems so faint compared to other forces. This idea isn't just speculation, it's a key part of models like the Randall-Sundrum theory, which imagines our universe as a membrane floating in a higher dimensional bulk. In this scenario, gravitons could move freely through the bulk while other particles are trapped on our brane. That's why we feel gravity's pull but don't see its full strength. It's partly escaping into the cosmic shadows. Testing this is tricky but not impossible. Scientists are hunting for tiny deviations in gravity's behavior at microscopic scales or anomalies in particle collisions at places like the Large Hadron Collider. If gravitons are indeed slipping into extra dimensions, they might leave behind subtle fingerprints, missing energy, or unexpected gravitational waves. Up next, we'll dive into another puzzle: how the geometry of hidden dimensions might hold the key to one of cosmology's biggest mysteries, the faint whisper of dark energy. Now, let's unravel another cosmic mystery. Why is dark energy so eerily faint? This brings us to the enigmatic cosmological constant, a number that has baffled physicists for decades. At its heart lies the vacuum energy problem. According to quantum theory, empty space should be bursting with energy, yet the observed dark energy is unimaginably weaker than predicted. Could hidden dimensions hold the answer? Here's the puzzle. When we calculate the energy of the quantum vacuum, the numbers are astronomically large, enough to tear the universe apart. But in reality, dark energy's effect is subtle, gently accelerating cosmic expansion. This staggering mismatch is one of physics' biggest unsolved problems. Enter extra dimensions. Some theories suggest that the geometry of these unseen realms could act like a cosmic pressure valve, siphoning off excess vacuum energy into higher dimensional space. Imagine a balloon with tiny pores. Some air escapes, reducing the pressure inside. Similarly, if vacuum energy leaks into extra dimensions, what remains in our universe might be the faint dark energy we observe. This idea ties into string theory's landscape of possibilities, where the shape and size of compactified dimensions determine physical constants. Certain Kaluza-Klein geometries could naturally suppress the cosmological constant to the tiny value we measure. It's like tuning a radio. The right dimensional configuration dials down vacuum energy to a barely perceptible hum. Critically, this isn't just mathematical speculation. If extra dimensions are real, their influence on dark energy could leave traces in the large-scale structure of the cosmos, subtle wrinkles in space-time or anomalies in how galaxies cluster. Future telescopes like the Euclid mission might spot these fingerprints, so while dark energy's weakness remains a profound puzzle, hidden dimensions offer a tantalizing clue, a cosmic fine-tuning mechanism written in the geometry of realms beyond our sight. Next, we'll explore how gravitational anomalies in our universe might hint at unseen forces tugging at us from other dimensions. Now, let's shift our gaze to another cosmic oddity, dark flow. Picture the universe as a vast ocean with galaxies drifting like ships on its surface, but something peculiar is happening. Observations reveal that hundreds of galaxy clusters are all moving in the same direction at incredible speeds, as if tugged by an unseen current. This mysterious motion, dubbed dark flow, defies our expectations. According to standard cosmology, matter should be evenly distributed after the Big Bang, with no preferred direction for large-scale motion. So what's causing this cosmic drift? One compelling explanation ties back to hidden dimensions. Imagine our universe as a three-dimensional sheet floating within a higher dimensional space. Nearby, there could be another brane, another universe exerting a gravitational pull on ours. Just as the moon's gravity creates tides on Earth, this neighboring brane might be gently dragging galaxy clusters along, creating the dark flow we observe. It's like feeling a breeze in a sealed room. You can't see the open window, but you know it's there. The stakes are high. If dark flow is indeed evidence of another brane's gravity, it would be the first tangible clue that our universe isn't alone in the higher dimensional bulk. Future missions like advanced galaxy surveys or precision measurements of the cosmic microwave background could either confirm this wild idea or send physicists back to the drawing board. For now, dark flow remains a tantalizing whisper from the hidden depths of reality, a whisper that might just rewrite our understanding of the cosmos. Next, we'll dive into how the holographic principle could reshape our view of dark energy itself. Now, let's unravel another layer of cosmic mystery: holographic dark energy. Picture the universe not as a vast three-dimensional expanse, but as a two-dimensional surface, like a movie screen projecting everything we perceive. This is the essence of the holographic principle, a radical idea suggesting that all the information in our three-dimensional reality might actually be encoded on a distant two-dimensional boundary. But how does this connect to dark energy, the mysterious force accelerating the expansion of the universe? Imagine the universe has a cosmic storage limit. Just as a computer hard drive can only hold so much data, the holographic principle implies that the amount of information in any region of space is proportional to its surface area, not its volume. Dark energy, in this view, could emerge from the tension between this information bound and the universe's expansion. As space grows, the available storage on its boundary stretches thin, creating a kind of pressure that drives acceleration like a balloon resisting as you try to inflate it further. This idea turns conventional physics on its head. Instead of dark energy being some exotic substance, it might simply be a side effect of how information is fundamentally organized in higher dimensional physics. Some theories even suggest that the holographic principle could explain why dark energy's density is so bafflingly small, a puzzle that has stumped scientists for decades. While still speculative, holographic dark energy offers a thrilling bridge between quantum gravity and cosmology. If proven, it would mean that the fate of our universe is written not in the stars, but on a hidden, two-dimensional surface we can't even see. Up next, we'll explore how extra dimensions might solve another quantum conundrum: the perplexing infinities of particle physics. Now, let's shift our focus to a puzzle that has haunted physicists for decades: the infinities of quantum field theory. At the heart of this mystery lies renormalization, a mathematical trick used to sweep away nonsensical infinite results when calculating particle interactions. But what if these infinities aren't just glitches? What if they're clues pointing to dimensions beyond our own? Here's the idea. In quantum field theory, particles are treated as point-like objects with zero size, which leads to calculations blowing up to infinity when particles get too close. But imagine if particles weren't confined to just our three spatial dimensions. If they could smear into extra dimensions, their interactions would spread out, softening those violent infinities. Think of it like smoothing out a crumpled piece of paper. The sharp edges disappear when you add more space to work with. This approach isn't just about fixing math. It suggests that the fabric of reality might be more spacious than we thought. Some theories propose that gravity's weakness compared to other forces could also stem from it, leaking into these extra dimensions, diluting its strength in our familiar three-dimensional world. While still theoretical, this idea offers a tantalizing solution to one of quantum physics' biggest headaches. If particles truly extend into hidden dimensions, it could rewrite our understanding of everything from the tiniest quantum fluctuations to the largest cosmic structures. Next, we'll dive into an even stranger possibility: time crystals, where the very notion of dimension takes on a whole new meaning. Now, let's step into a world where time itself takes on a strange new shape: time crystals. Unlike ordinary crystals, which repeat their atomic patterns in space, time crystals repeat their structure in time, creating a never-ending loop of motion even in their lowest energy state. This bizarre behavior was first proposed by Nobel laureate Frank Wilczek in 2012, and it challenges everything we thought we knew about equilibrium and symmetry in physics. Here's the twist: time crystals don't just defy classical physics, they might also be whispering secrets about hidden dimensions. The way these structures oscillate without energy input suggests a kind of symmetry that could only exist if higher dimensions were influencing their behavior. Imagine a clock that ticks forever without winding, its gears turning in sync with dimensions we can't see. That's the eerie elegance of time crystals. What makes this even more fascinating is how these structures could bridge quantum mechanics and cosmology. Some researchers speculate that the same higher dimensional symmetries governing time crystals might also shape the fabric of spacetime itself, offering clues about the universe's underlying geometry. While still in the experimental stage, time crystals have already been created in labs using chains of ions or superconducting qubits, proving that this once theoretical idea is very real. Their existence opens a door to technologies we can barely imagine, from ultra-precise quantum sensors to entirely new forms of computing. Up next, we'll venture into one of the most controversial ideas in modern physics: the possibility that our entire universe is nothing more than a simulation running in a higher dimensional computer. Now, let's take a mind-bending leap into one of the most debated ideas in modern physics: the possibility that our entire universe is nothing more than an advanced simulation running in a higher dimensional computer. This isn't science fiction. Some of the brightest minds, including Elon Musk and philosopher Nick Bostrom, have seriously considered the simulation hypothesis. The core idea is simple yet staggering. What if our reality is just an ultra-realistic program created by a civilization with technology so advanced it's indistinguishable from nature itself? Here's where hidden dimensions come into play. If our universe is a simulation, the computer running it would likely exist in a higher dimensional space beyond our perception. Think of it like a video game while the characters inside the game experience a flat, two-dimensional screen. The programmer exists in a three-dimensional world with far greater control. Similarly, a higher dimensional creator could manipulate our reality in ways we can't even fathom, tweaking the laws of physics or inserting glitches that appear as quantum anomalies. What's eerie is that some scientific discoveries seem to support this idea. Take quantum mechanics, where particles behave differently when observed, almost as if the universe is optimizing processing power by only rendering what's being watched. Or consider the mathematical precision of the cosmos. Constants like the speed of light are so finely tuned, it's as if they were coded by design. Even the holographic principle, which suggests our three-dimensional world might be a projection from a two-dimensional surface, fits unnervingly well with the simulation theory. Of course, not everyone is convinced. Critics argue there's no direct evidence and the hypothesis is unfalsifiable, meaning it can't be proven or disproven with current science. But that hasn't stopped researchers from looking for clues. Some propose that if our universe is a simulation, it might have tiny computational pixels at the smallest scales of space-time, or occasional errors like cosmic rays that could be glitches in the code. Whether you find the idea thrilling or unsettling, it forces us to ask profound questions. If we're living in a simulation, who or what is running it? And if higher dimensions hold the answer, could we ever break free and glimpse the true nature of reality? Up next, we'll explore how hidden dimensions might hold the key to one of physics' greatest mysteries, the arrow of time, and why it only moves forward. Now, let's turn our attention to one of the most puzzling mysteries of the cosmos: why time only moves forward. We've all experienced the relentless march of time, but what if hidden dimensions hold the key to understanding its one-way flow? This is where the arrow of time meets the enigmatic world of extra dimensions. At its core, the arrow of time is tied to entropy, the idea that systems naturally evolve from order to disorder. Think of a shattered glass that never reassembles itself, or an ice cube melting in your drink. These everyday examples highlight time's irreversible nature. But here's the twist. Some physicists propose that higher dimensions could be shaping this behavior in ways we can't directly observe. Imagine time as a river flowing through a landscape of hidden dimensions. In this picture, entropy isn't just a property of our three-dimensional world, it's influenced by the geometry of these unseen realms. Just as gravity warps space-time, the structure of extra dimensions might guide time's direction, creating the asymmetry we perceive as the arrow of time. One compelling theory suggests that the expansion of the universe, driven by dark energy, could be stretching these hidden dimensions in a way that locks time into its forward motion. If true, this would mean the arrow of time isn't just a local phenomenon but a cosmic feature woven into the fabric of multidimensional space. But why does this matter? Understanding time's irreversibility could unlock deeper truths about the universe's origins and ultimate fate. If hidden dimensions are steering entropy, they might also hold clues about the conditions at the Big Bang or the distant future when entropy reaches its maximum. Of course, this idea isn't without its challenges. Critics point out that we lack direct evidence for extra dimensions, let alone their influence on time. Yet the possibility remains tantalizing, a reminder that the mysteries of time and space might be far more interconnected than we ever imagined. As we ponder these ideas, we're left with a profound question. If time's arrow is shaped by dimensions beyond our perception, could we one day find a way to navigate them, or even bend time itself? Up next, we'll dive into the cutting-edge experiments that could finally reveal whether extra dimensions are more than just theoretical marvels. Now, let's shift gears and explore how science is actively hunting for evidence of these hidden dimensions. One of the most exciting frontiers in this search lies within massive particle colliders, where physicists recreate extreme conditions to probe the universe's deepest secrets. At the heart of this quest is the Large Hadron Collider, the most powerful particle accelerator ever built. By smashing protons together at nearly the speed of light, scientists hope to catch glimpses of extra dimensions through two key phenomena: microscopic black holes and mysterious missing energy. Here's how it works. If extra dimensions exist, the collider's incredible energy might briefly warp space-time enough to create tiny black holes, so small they'd vanish in an instant. These fleeting specks would be smoking gun evidence that gravity is leaking into higher dimensions, just as some theories predict. Alternatively, researchers are watching for collisions where energy seems to disappear. This missing energy could be carried away by particles moving through dimensions we can't see, like a ball rolling into an invisible tunnel. The LHC's detectors are fine-tuned to spot these anomalies, which might otherwise go unnoticed. While no definitive proof has emerged yet, each experiment narrows the possibilities. Some models suggest we might need even more powerful colliders to uncover certain types of extra dimensions. Others propose that subtle quantum effects in existing data could hold hidden clues waiting to be decoded. What makes this search so thrilling is its tangible nature. Unlike purely theoretical work, these experiments offer a direct line to testing wild ideas about multidimensional reality. Every collision is a chance to rewrite our understanding of the cosmos one particle at a time. As we close our journey through 30 mind-bending theories, remember this: the universe's greatest mysteries may be hiding in plain sight, just beyond the dimensions we know. Whether through colliders, cosmic observations, or bold new mathematics, the hunt continues, and the next breakthrough could come any day. What's your favorite theory about hidden dimensions? Share your thoughts below, and don't forget to subscribe for more deep dives into the universe's secrets. Until next time, keep looking beyond the visible, because reality might be far stranger than we imagine. As we wrap up this cosmic journey through 30 theories about hidden dimensions, let's take a moment to reflect on just how profoundly these ideas could reshape our understanding of reality. From the intricate vibrations of string theory to the holographic projection of our universe, each concept challenges the very fabric of space and time as we know it. These aren't just abstract musings, they're potential keys to unlocking the universe's greatest mysteries, from dark matter to the birth of existence itself. What's remarkable is how these theories bridge the gap between imagination and science. They push us to rethink gravity, matter, and even consciousness through the lens of dimensions we can't yet see. Whether it's brains colliding in higher dimensional space or particles slipping into unseen realms, the possibilities are as thrilling as they are endless. Now, we'd love to hear from you. Which of these theories resonated most? Do you think hidden dimensions are the missing piece in physics, or is there another explanation waiting to be discovered? Drop your thoughts in the comments below. Let's keep the conversation as expansive as the cosmos itself. If this deep dive into the universe's secrets left you curious for more, don't forget to hit that subscribe button and ring the notification bell. There's always another mystery waiting just around the corner, and we'll be here to explore it together. Until next time, keep questioning, keep wondering, and remember, the universe is far stranger and more wonderful than we've yet imagined.